Hello and good afternoon. My name is Mohamed Elzeadani. I'm the chair of the Second Young Members Subcommittee, and I'm delighted to have with us today Alessandro Beghini from SOM, who will be giving a presentation on the Los Angeles County Museum of Art, Architectural Innovation through Base Isolation and Exposed Concrete. Yeah, just a few housekeeping rules before we begin. Please keep your video cameras off and microphones on mute for the duration of the presentation. Please also note that there will be a Q&A session at the end of the presentation, but if you have any questions in the meantime, then feel free to drop them in the chat. And also please note that this session is being recorded and will be uploaded to our second YouTube channel. Therefore, by joining this call, you consent that any views or information you share will be made public. Just a quick announcement. So the second Young Member Subcommittee will be taking part in the Chain Bristol 2026 event. So this is an event that is intended to bring together various professional engineering societies and will be taking place on the 11th of February at the UWE Frenchay campus in Bristol from 6 to 10 p.m. So the intention of this event is to encourage networking and also exchange of ideas between different engineering societies. And there will be a talk by each of these societies, including SECIT. So if you are in or near Bristol on the day, then please do drop by. And for our speaker today, Dr. Alessandro Beghini. He's a Senior Associate Principal at Skidmore, Owings in Merrill. His project portfolio encompasses a wide range of award-winning projects, from some of the world's tallest buildings to sculptures and specialty structures. Alessandro has established an expertise in delivering structural solutions that are efficient and elegant, working alongside the architectural and building services team. He was part of the team leading the structural design for the Tianjin CTF Finance Center in China, the world's eighth tallest building at an outstanding height of 530 meters. Other significant collaborations include the work with Atelier Peter Zumthor for the structural design of the Los Angeles County Museum of Art, and numerous collaborations with world-renowned artist Janet Ashleman, including the current sculpture in Columbus, Ohio, and Earth Time Korea, among several other temporary installations. So Sandra is joining us today from California, and Sandra is very early in the morning over there. So thank you for, I appreciate the effort for joining this call today. And I hand over to you, Alessandro.
Well, thank you. Thank you for having me here. So I'm going to start sharing my screen. You should be able to see my screen.
Yes, I
All
can.
right. Perfect. So thanks again for the introductions, and it's a pleasure to be here and speaking with you today about the Los Angeles County Museum of Art, which is a project I've been working on in the past, I would say 10 years, and it is coming finally to completion in the upcoming four months. And the project really presented several challenges, but at the same time offered many opportunities, in particular, opportunities for innovation and innovation through the base isolation system and through the unique type of concrete, the architectural exposed concrete that was used throughout the project. So before going into the specifics of this project, I'd just like to give you a very brief introduction to our studio and the type of projects we worked on. So SOM is an interdisciplinary studio of architects, engineers, urban planners, interior designers, and really the objective here is to really have a positive, innovative impact in design while really being respectful for the environment. And as a studio, we have 11 offices around the world. So SIM was founded in Chicago and then expanded to New York. And now we have offices in San Francisco, where I'm based, Los Angeles, London, Dubai, and so on and so forth. Personally, I've been in the Chicago office for about 10 years first. That's where I started my career. And then I moved on to San Francisco when I've been for the past 10 years. And one of the most important aspects of our studio is really the interdisciplinary nature of our work. So in the office, we have engineers, so structural engineers, we have architects, interior designers, urban planners. So when a project arrives in one of our offices, we can approach it from different perspectives. So as a result, there's a design ethos that has really a structural and functional core from the start. So the design, for example, of a tall building, as well as a table or a chair, is really the result of a continuous dialogue between an engineer, an architect, and a builder. And really, this dialogue is essential so that the project really can get constructed, right? Is well resolved. And the interdisciplinary nature of our studio also means that the design of the project is not only linked to the experience that the architect is creating, but it's also the expression of the forces that are acting on the system and really the type of work, the type of methodologies that are used to build the structure, which are then oftentimes expressed throughout the design itself. And our portfolios covers a variety of types. We have, you could be working from very large airport, and for example, here there is a picture of the Mumbai airport. You could be working on courthouses like in Los Angeles, or renovation projects. So really a variety of projects, as well as a lot of different experiences from the different disciplines that are under the same roof, including the structural engineering, where I'm, which is my department, and then architecture, sustainable design, and really and graphics, right? So just taking into account the lens of our approach to design, let's dive into the project I'm focusing on today, which is the Los Angeles County Museum of Art. So this is a picture of the upcoming building within the context of the LACMA campus. It is actually it has been many years in the making. I was mentioning earlier about 10 years we have been working on this project, and it is just one of the latest addition to a number of new structures that were added over the years. And you can see them here scattered on the campus. There is the Resnick Pavilion, which was designed by Renzo Piano, and then the one that is in spherical in form, which is the Academy Museum of Motion Picture. And you can see, the LACMA building for the permanent collection is at the center with that amorphous shape. And if you look at the past, if you go back a few years back to 2006, this is what the LACMA campus looked like back then. And there were a few pre-existing buildings which were demolished prior to the starting of construction. Essentially, what the building I showed you in the previous picture occupies is the kind of the area in blue, in addition to crossing the street, Wilshire Boulevard, which is a major artery in the city of LA. So it crosses that street on the south and goes into a portion of what was previously a parking lot. And the original complex included, four buildings that had multiple functions back then, but that became a bit obsolete and weren't really useful for the museum, and that's the reason why they decided to move on with this new building for the permanent collection. And the project really started with the search for the architect, and Pritzker Prize winner Peter Zumthor was selected as the design architect for the project. So maybe a few words about Peter Zumthor and his approach to design. So first of all, a few projects, major notable projects by Peter here, and his design philosophy really centers on creating deeply sensory, atmospheric, and emotional spaces that connects with their specific places, right? I mean, he's literally looking at the materials, the history of the place where he's designing. He wants to emphasize the experience, and also there's a lot of attention to craftsmanship, to honesty of material. So it's a very, very interesting perspective, and he really believes that architecture should engage all the senses, right? Using textures, light, sound, right? Creating this holistic experience. And the design process itself took about 5, 6 years before we could actually start the design. So it was a very meticulous process, and it was really interesting working with him because the approach itself is very much rooted, like you can see here, in physical models, right? There's a lot of work with paper, right? And so the use of physical models, the use of paper allows for a very deep focus and also interesting spatial explorations, right? Because when you're in front of a model, you can see very clearly if there are opportunities for something that you may not be able to capture when you're looking at just a digital model through your screen. And this is just a picture of Peter in his studio where he places the models, very large scale models, on top of the stills so that they're actually at eye level. And so you can actually see them from the point of view of an observer that would be experiencing the museum when constructed. The design process went through a series of iterations. This is one of the first model we worked on, and you can immediately distinguish a few important features of the design. The design concept features this elevated single-level art space, which is sitting atop the porous ground floor, and therefore it eliminates any hierarchy in the visitor experience, which is different from more traditional multi-story museum and from what the older buildings that were there for LACMA were. Essentially, when you typically visit a museum, you could go and visit, say that you want to see the Impressionist painting. So you go to the Impressionist room, and then you want to see Japanese pottery. You may need to go, maybe the Impressionist is on the 10th floor. May need to go down to the ground level, go to a different building, go back up another building. This automatically sets a hierarchy because usually what's on the ground floor of a museum is what's most visited because it's most accessible, right? I mean, people will go there. But here, by placing everything on the same level, well, there is no more that hierarchy, and you can easily access, once you obviously go up on that level, that single level, you can access all the collections and all the pieces and all the exhibitions at the same time. So it's a very interesting approach to the experience of the museum. This is a plan view of that same concept with a series of boxes that are clustered around the center. Another important feature of the design that you can see here is that actually the building spans across Wilshire Boulevard, as I was saying earlier. This Wilshire Boulevard, this is on the south side of this building, is really a major roadway in LA. But what that does is that it makes the building partly a building, but partly also a bridge because you're spanning this major road. And like I was saying, so we just saw one first iterations. There were several iterations after that. So for example, you can see here, this is the iteration after 1 year. After 1 year, you can already see that the quality of the plan is very different from the first one. You can see here now that those boxes, those towers, which are the towers that support that main exhibition level, are very different. They're polygonal, first of all, and they are more scattered in the plan, right? It's a very, very organic nature that is developing. And just looking for the same scheme, if you look at it in an elevation, you can see here what we call art towers. These are the buildings that essentially are protruding through the exhibition level, which is the one elevated, and they house essentially the vertical transportation elements. So you can see there's elevators, there's stairs, there's mechanical shafts, right? Inside those art towers, and essentially the building itself, which has the exhibition level and then the roof, has components that are spanning between these art towers or cantilevering off the art towers, in addition to the bridge that is spanning across Wilshire Boulevard. So iteration started from 2015, then we moved on in 2016, right? So let's look at the next iteration. So this is the last iteration, right? And there were some other iteration in between, just to give you a flavor of the iterative process, and refinement that we went through for the design. And this is the iteration that is coming from the summer of 2018, where you can see now that from the polygonal shapes, now we are in rectangular shapes, rectangular form, a more refined shape of the perimeter of the edge of the exhibition floor. And what you can see also is that not only we have what we call art towers, which are the main towers that go down to the ground, but also scattered throughout, there is a series of what we call chapel galleries. Let me just go to the next one. It will become more clear. So essentially the towers, the boxes that actually reach the ground are the ones that are filled in here, and they're color coded by what we call neighborhoods, right? And then connected to them there is a series of boxes which are not filled, right? Again, different colors, but they're connected back to the main towers. And the purpose of these empty boxes is really to stiffen the sandwich of the exhibition floor and the roof to make sure that, given the long spans that we're having here, we would be able to control the deflection and we will be able to design for strength. And you can see, purple is a neighborhood, and there is cyan is a different neighborhood, yellow is a different neighborhood, and so on and so forth. So what is given this architectural iterations, in parallel with the architectural iterations, there were several structural iterations that came with it. And so this is just a very simple, one of the early on structural sections, but it's still very powerful because it really explains the fundamentals behind the concept of the structural system. So what you can see here is that we have these reinforced concrete towers, right, which are made up of reinforced concrete shear walls that represent the primary lateral system for the project. And the towers come down and sit on top of isolators, right, which are at the very bottom there. And the isolators are providing the building seismic isolations. And we'll talk a little bit about seismic isolation just in a few minutes. Obviously, as you can imagine, we are in Los Angeles, very high seismicity, and we are talking about a museum. So important, valuable, invaluable content inside the museum. So to protect it, we made the decision to go down the route of seismic isolations. The tower with the shear walls represent the lateral system, and the gravity system uses post-tension reinforced concrete to support those, as you can see, those very long cantilevers projecting from the towers, right? And so we have these conditions spanning across multiple towers and then the bridge across Wilshire Boulevard. And the floor sandwich itself, or the roof system, is composed of a top and bottom slab connected by a vertical reinforced concrete ribs, essentially. And so the sandwich itself is very deep and provides enough stiffness. In addition to having that, you can see the chapel gallery, which is for some form of a V&D panel in between the roof sandwich and the floor sandwich. And then the cavity spaces that are created within the roof sandwich and the floor sandwich are then used for mechanical purposes as a plenum for the mechanical system. So this is just another, image of the final plan geometry of the building, which ended up from a structural point of view being a two-way of interconnected ribs. So what you see in this diagonal pattern is all the ribs that are connecting all the way across the plan, which is a very large structure, because if you think about it scale-wise, is about every one of those diamonds is about 8 to 10 meters in dimensions, and then overall the length of the building itself is about 200 or so meters. So very, very long, with cantilevers that in some of the worst conditions could be up to 30 meters. So 30 meters cantilevers are very significant and obviously require this very robust structural system. You can see also that this two-way grid of diagonal ribs covers the entire plan and are coordinated with the geometry of the towers and the chapel gallery. So everything is working together geometrically to create and support the vision, the architectural vision. Prior to starting of constructions, we had a number of renderings that could show what the building would look like. So these are the initial rendering of the spaces. Obviously, towards the end, I'll show you some of the construction photos and kind of where we are in terms of construction. But just to give you a sense of what this final spaces will look like, again, architecturally exposed concrete. So going back to what I was mentioning in terms of the design philosophy, honesty of material, nothing is hidden, everything is exposed. Even in the ceiling, you can see those triangular lines are actually the lines of the formwork, and the formwork that was used was triangular formwork. And so it expresses even more that those rib lines that are hidden within the soffit of of the roof, and they become expressed, right, into this geometry. You can see that all those openings for lights were properly coordinated because obviously they need to deal with the rebars or the PT that was inside the museum. This is another picture of the spaces, more pictures, and essentially the whole building is defined by three materials. There is concrete, there's glass, and then there is bronze. You can see it cast in the mullions, and you can see it from the outside. We also went through several iterations of colors for the concrete. This is the final one of the final concepts and rendering for the building. So let's take a look at, obviously, with you, I want to mostly focus on some of the structural aspect of the project. There is a lot, obviously, in the architectural discussion that could be said, but let's focus more on the structural aspects. And there's three big chapters from a structural point of view that we can talk about today, which is the first one is about the post-tensioning and the gravity system. The second one is going to be about the lateral system and the base isolation. And the third one, I'm just going to show you some of the construction, the most meaningful construction phases and the construction sequencing for the project. So the first step, looking at the post-tensioning and that was used in the project for the gravity system, this is just a picture from our analysis model. We used LUSAS as a software to analyze the post-tensioning. We actually had two primary structural models. So the LUSAS model was used for the gravity system and the analysis of the gravity system. And then we had an ETAPS model in a completely separate, which was used primarily to do the lateral system analysis. And the LUSAS models, in order to do analysis of post-tensioning, you need to account for a number of factors. That is, in particular, when you deal with concrete, what you're concerned about often with long cantilevers is really long-term deflections. And so you need to be able to simulate creep, shrinkage, pre-stress losses, and a number of other phenomena that occur when you're dealing with PT. And this is just a picture of the model. You can see here in cyan on the top, you can see the PT tendons, those light blue cyan colored lines. Those are the PT tendons in the ribs. And then on the picture below, separated, from the others, you can see those boxes, that's powers and chapel galleries, and all the PT tendons that are in the walls. So if we want to break down the PT system a little bit more, this section is helpful in understanding, how the whole system works. First of all, an important aspect of the structural system is the extensive use of the balance or double cantilevers, where essentially, whenever you have a cantilever on one side of a tower, we try to balance it with a cantilever of similar length on the opposite side, right? So that when you have a balanced cantilever, you just don't have a net moment that is going into the tower and causing obviously a net moment at the base of the tower itself, right? Not only that, but the post-tensioning cable bundles are introduced inside the shear walls. You can see here those black lines are essentially cables, post-tensioning cables. So we have the post-tensioning cables inside the shear walls to counteract gravity forces. And these post-tensioning cables are laid out according to the principal stress directions inside the wall. So an analysis is conducted to understand what the natural flow forces will be inside the walls, and then you would follow that natural path in order to lay out your cable inside the wall. As you can see, there's also post-tensioning cables that stay high, either high in the roof sandwich or high below in the exhibition floor sandwich, right? And those are there to support the cantilevers and the long spans within the building itself. So there is a clear hierarchy. And that hierarchy is really organized. So we have a slab PT, which is meant to support, PT slabs spanning between ribs. And those are, generally speaking, tendons of half-inch diameter, about. And that's meant to counteract the behavioral slab itself. Then we have the slab is spanning two ribs. And these ribs, again, have PT tendons inside the rib itself, and those drapes they drape in order to follow to compensate for the gravity loads inside the ribs, and then the wall PT, which is bigger bundle PT system. So very extensive use of PT. Now, how do we design the PT? Well, we take our losers model, and what we do, we really set up a series of sections. So, for example, say that you need to design a rib within the sandwich of the roof. Well, you would set up all, you can see these planes, these right planes, which is a series of cross section that you would integrate along the beam, which would allow you to know what the forces are at each, every so often, say every meter or 2 meters along that beam. And then you would integrate and then extract them and then design them as part of a bigger process or script that allows you to take every single one of them and process them. As I said, uh, one of the key aspects in the design is has always has been from the very beginning, the long-term deflections, right? And this is just a counter plot that shows you just a map, like a heat map of deflections within the building, and is extracted again from that LUSA software. When we look at long-term deflections, we are looking mostly at the deflections that are caused by the self-weight of the structure, together with the sustained, what we call sustained loads, sustained dead loads, which are superimposed dead loads on the building, and whatever would factor in and should be considered for this long-term view of the project. And obviously you're looking at a very long span. So for example, this is 3,000 days, so very far in the future, and needs to account for creep and shrinkage, right? And you can see here, for example, that the highest cantilevers, which are in red here, are the highest deflection in red are at the bridge across Wilshire Boulevard or at the longest cantilevers. In particular, there is a couple of spots on the south side of the building where you can see that 2.33 or the 1.93 inches, which are in the order of 60 to 70 millimeter essentially. And those are the longest cantilever, or we have the bridge. So those immediately became the hotspots that we had to pay close attention in order to mitigate the long-term deflection. Not only that, but in order to mitigate long-term deflections, we decided to introduce a compensation program, what we call a camber program. I'll show it to you in a minute. Now, in addition to monitoring the long-term deflections, we also looked at immediate elastic deflections, right? So those immediate elastic deflections have more to do with the live load deflections, which comes from occupancy, right? Meaning people occupying the building, visitors, right, experiencing the building. But those loads are typically not sustained, meaning they are short term, right? Because they're not always there. And so they're not always imposing, a load on the building itself. And also those live load are much smaller. So really the biggest component of load here is coming from the self weight and whatever art content that is inside the building. When we look at deflections, I mean, the absolute deflection, so those 60 to 70 millimeter I was mentioning earlier, is not the only thing that we look at. We need to also think about the systems that go into the building. So, for example, thinking about the exterior wall system, so the glazing, right, that we saw in those interior views, interior renderings. So the glazing itself, right, is sitting at the edge of the exhibition floor. So this is a plan of the exhibition floor. And as you can imagine, I mean, the glazing has mullions that support the glass, and the mullions are connected to the soffit and the roof sandwich. And so what we need to monitor is really the differential deflection between the roof and the exhibition level, because that differential deflection enters into the detailing of that exterior wall. So we're going to have a joint at the top of the exterior wall, and we want to make sure that at any point in time we don't have too big of a gap or too small of a gap, because obviously it would cause problems. And therefore we were closely monitoring this differential deflection. And you can see here that the biggest differential deflection we were having, it was again at those hot spots of the longest cantilever, and it was in the order of 25 to 30 millimeter. And And I was mentioning, for the deflection, in order to compensate, right, for the large deflection, we introduced camber. So camber essentially is the camber program essentially instead of building the slab or the ribs flat, you actually build them with a little higher, right? So that by the time over time it flattens, right? So the maps that we saw earlier, right? The heat map which had deflection up to say 60, 70 millimeter, right? Eventually, if you build a little bit higher, then slowly over time comes down, it becomes flat. So we produce maps that could be used by the contractor in order to be able for a series of points which we agreed upon, right? We agreed that we will give, at any one of these points, you can see this bubble plot. A bigger bubble is a bigger camber, and we provided to the contractor a camber in the order from here is 3 millimeters to 20 millimeters, right? So essentially, everywhere the formwork was at a different elevation by a few millimeters, so that then when they casted, it would be casted in this higher elevation, and then over time it will come down. And then just to conclude this discussion on the post-tensioning, just a couple of details again, speaking to that sandwich I was mentioning. This is the typical sandwich. So essentially, you have the top slab and a bottom slab and a rib that is in between. And you can see very visible here. There is PT tendons that are running. There's reinforcement inside that rib. There is reinforcement inside the slab, and there's a topping slab for the exhibition floor where you be walking. And then what you see is for the bottom slab, you would see the soffit, and in that cavity is where all the mechanical equipments and other MVP services will run. So it was very close collaboration with MVP consultant. We have the mechanical engineer, electrical engineer, the plumbing engineer, in order to make sure that everything could fit. Not only that, but once you start running services within this cavity, you also need to make sure that you have openings in the ribs, right? We saw in the plan earlier that we have these ribs running on a diagonal pattern, so essentially covering the entire floor plan. And therefore just making sure that we would have these openings. This is an example of openings, and that those were properly coordinated and detailed. So all these black lines now represent the proper detailing with trim bars, and strengthening of the corners of the opening, and making sure everything is accounted for. So the next chapter I want to talk about is the seismic protection. As I was mentioning, seismic protection was one of the key aspects of the design from the very beginning. We're designing a museum, invaluable art content inside the museum. So how do we protect the art from the large seismic forces that are occurring in the area? And just to give you a sense, scale, this is a map of the local faults in the LA area and possible events. So you can see that there is a combination of local faults capable of magnitude of 7.0 or greater than 7 events, and then there is a Sant Andreas fault, which is capable of magnitude 8 events. So it's very high seismicity, which really affected, the design from the very beginning. And so after a series, of discussions and back and forth, we decided eventually to go with triple friction pendulum bearings for an isolation system, horizontal isolation system. These are very large bearings, probably amongst the largest bearings ever fabricated, because they're about 3 meters in diameter, and they're capable of 1.5 to 2 meters of displacement. So they're really large. And there's not only horizontal seismicity, I'll show you in a second, but there's also vertical seismicity. And so we also introduced nonlinear viscous dampers for the vertical vibration. So let's take a closer look at the numbers. And I like to do it with the spectral accelerations, essentially for the site. You can see here the magnitude of forces we're talking about, the horizontal MCE, maximum credible earthquake, that is capable of over almost up to 3G of acceleration in terms of horizontal acceleration, but the vertical spectrum as well. I mean, it's pretty significant, as you can see here by the blue line, right? And then you also here we put also the design spectra for the design. So taking if we had gone down the route and we looked at it, we looked at the fixed base building for our building, we are in our period would have been in the order of zero point 0.2 or 0.25 seconds or something. So pretty rigid because essentially it's a one-story structure, right? I mean, you have just the one exhibition level. So it would have been pretty rigid. And so at that period, you would have been in the order of 2.5 Gs of acceleration, which is pretty considerable, right? Not only that, now imagine having a fixed connections. I mean, what that would do to the art, right? In case actually an earthquake would come, you would have to then base isolate every single art piece, right? Independently within the exhibition level. So why not, introducing the base isolation system? So by doing that, what effectively you're doing, you're lengthening the period, right? So you see that when you lengthen the period, then you all of a sudden, the forces that are experienced by your building go down dramatically because from the 2.5, you're going down to less than 0.25 G. And all of a sudden, your building is protected, the art is protected, and it was the best solution that we went with. As I mentioned, the vertical spectrum is also very high because we have accelerations in that for the cantilevers in the order of 1 G, and thus the reason to use vertical dampers in the design. So let me start from the vertical damper. So just some of the analysis that we conducted here, you can see here a little video. If you don't couple, you can see here in blue and this is a picture from ITAS model. In blue, you have the exhibition level, right? The lower slab, the lower sandwich, and then you have the roof level, the upper sandwich. And what we're doing here on the left, we are monitoring using nonlinear time history analysis. We are monitoring the displacement of the yellow dot, which is essentially the reference point back at the tower, which vertically the tower are not moving considerably. And then they're essentially moving with the ground. And then we have the movement in red of the cantilever. Because there is a differential between the red and the yellow, obviously you have significant vertical acceleration. What happens when you isolate them? What happens when you combine them using a vertical dampers? You can see here now in green, we have the vertical damper. Then the differential deflection between the top and the bottom is significantly mitigated. Just take a look at I'm going to go a little bit back and then forward again. But take a look at the video doesn't want me to go back, but take a look at the time history, the vertical acceleration in G, and here you see how it's diminished. So not only we are combining, but we are reducing significantly the relative movement between the two, which obviously is a significant reduction of accelerations that is experienced by the exhibition level, and of course the forces that are acting on the artwork that is inside the museum. Just showing you the typical detail. Actually, these dampers are concealed in the soffit of the roof sandwich, and so they've been built, and they're right above the mullions that are supporting the glazing. So the mullions penetrates the lower slab in the roof sandwich and then connects the viscous damper inside the sandwich. The other important aspect is the horizontal isolations. Being here in San Francisco, as you can imagine, we have experience of using base isolation in multiple buildings. The system that we went with is triple friction pendulum isolators. And you can see here, this is some of the testing that was conducted. The isolator itself is made up of a series of plates that can essentially slide relative to each other. And the three plates are there to mitigate different level of earthquakes or seismicity, right? So if the seismicity is low, the first plate is engaged, and then as the seismicity becomes bigger and bigger, that internal steel element touches the edge, the rim of the subsequent plates and engages it. So there's this system of plates that really allow for large movement. And this is just a picture of the analysis that was conducted in ETABS. As mentioned earlier, we had two models at any point in time. We had the ETABS model that would be used for the lateral analysis, the global model, and then we had the LUSAS model mostly for the gravity system. And if you compare the fixed base model compared with the base isolated model, you can see here just, how the behavior is significantly different. So just in this little video, you can see the base isolated model. Essentially, the entire building as a unit is sitting on top of these isolators, and we had 40 isolators because we had essentially 10 towers, right? The 10 out towers, and each out towers is a box, and at the corner of this box, there would be those four isolators, and you can see here very large movement, while the fixed base model essentially is very rigid and is transferring all the loads back to the art and the interior content, right? Okay. As part, of the process, we monitor the performance of the system. At any point in time, we were looking at the design earthquake, right? And the maximum, at the MCE level, maximum earthquake. And we were monitoring how we would be able to reduce the drifts and the acceleration. So the drifts were significantly reduced by using the base isolation, in particular the differential drifts that would occur between the ground level and obviously the exhibition level, and also the acceleration. So the accelerations you can see here, the floor accelerations were significantly reduced, and that turned into a significant benefit for the entire building. Obviously, using base isolators, we went back and forth with the fabricator of the base isolators, but also we had to validate that these isolators could take the large forces that would occur on them when they are eccentric. So you can see here, this is a picture from our finite element model of the picture in an eccentric position. So as you can imagine, right? I mean, not only you have this couple that is a very, very large force that is going through the system, right? And these are, like I said, very large forces that are going through, and you need to ensure that the isolator can actually take it. But not just the isolator, because when the isolator is a pure pin, right? So you can already transfer moment through this isolator. So the moment is transferred. Every couple we have caused by this eccentricity needs to be transferred by the structure that is either above or below the isolator. In this specific case, it has to be the structure that is above the isolator. So the isolators were connected using a series of very large and deep beams. You can see here in this dark gray. These are the beams that are above the isolator. And essentially, we loaded these beams with that eccentric load, so this eccentric moment, to ensure that we would have a proper path, right, through the isolator. Then the isolator itself at the base is sitting on top of a pedestal. And so we need to take that load from the top all the way down to the pedestal. So again, another very detailed finite element analysis to understand what the load path, and again, this is a contour plot showing, the transfer of load, continuous load from the shear walls above through this very thick beam connecting the isolators down to the pedestal itself. And then taking that load, significant load, and converting it into, detailing, right? I mean, there has to be enough rebar that in order to be able to take these significant forces all the way down, and modeling them. So there is the drafting, and the 3D modeling of all the components of all the rebars is another important chapter of the conversation, in order to make sure everything fits when it's constructed. And also testing. We did testing, full-scale dynamic testing of the isolators. This is in the facility of the fabricator of the isolators, and you can see, on the right, the scale, that was used. And this is again some pictures from the on the left from the fabricator's facility. It's very large, these isolators. And then on the right, a couple of our engineers back on site at the time when this was implemented. The last 4 minutes, 5 minutes, I like to dedicate a little bit to the construction itself, construction sequence, and a couple of pictures of construction very quickly. As you can imagine, as part of the construction itself, what's another important chapter is how do you actually build a building? What is the sequence of events that need to occur? What do you build first? What do you build second? When do you stress? So these are all questions that are, and needs to be considered very carefully, because the sequence of building affects the way things are shrinking, right? So concrete shrinks, and so you need to typically allow for gaps and joints in order to be able for the building to breathe, right? Because if you lock the building, too soon, what would happen? Concrete cracks, right? So even a slab, when it's shrinking, if you don't allow it to breathe, it would crack. So a lot of consideration went into, okay, how do we sequence our casting? So what is the sequence of pouring? For example, a slab, and we have different slabs here, right? We have 4 slabs all the way up. And how do we leverage the isolator themselves in the process of building the building to allow for it to breathe, right? Because there is no joint. So this is a very long building, 200 meter plus long, without any joints, construction joints, to let it breathe, right? So it's just one monolithic building. So we decided to leverage the isolators and the sequence of locking and unlocking the isolators, right? So when they come to site, the isolators are locked because they cannot slide, right? But as soon as you unlock them, right, they can actually slide. And so if the building above is shrinking and moving, right, and breathing, then these isolators allow it to breathe and move and shrink, accordingly. And so we really studied closely what was the sequence, and you can see it here, if you lock the isolators at tower F, I mean, what would happen? How much movement would you get? And in which direction does the movement go relative to the shrinking that is occurring? So, and we monitor the shrinkage not only at construction, but after construction. What happens 5 years after construction, right? And we put even instrumentations, right? And so the whole idea is that as you're unlocking the building, everything is shrinking towards F. And so even the furthest out tip of the building will move towards that central tower. And we had these tools in place to be able to monitor that the shrinking was occurring, and obviously to our satisfaction, it was occurring in the sequence we were expecting and in the magnitude that we were expecting, with larger movements obviously further away because the elements are further away as we are shrinking. They're converging right towards the center. You can see here there are dots, and the relative. And as we are monitoring this movement, we are also monitoring the relative displacement. Again, the exterior wall is very sensitive to the detailing and the way the detailing was conducted. And so we looked at the numbers of relative displacement to ensure that the detailing and of the exterior wall system could take this differential. So just the final just a few construction photos. This is where we started. This is the site at the beginning before we started any constructions. And throughout construction, I mean, there were obviously key moments. You can see here when the first isolator went in, and this is Peter that wanted to take a close look at the isolators when it was installed, together with some of my colleagues from the structural group on the right. All right, you can see here again the scale of the isolator. There's some beautiful imagery that you can find online, and this is just a picture that I found online. You can see in red, the red lines are actually the PT tendons, and you can clearly see also visible the ribs, the diagonal pattern of the ribs on the building during construction. You can see here again, I mean, these are all PT tendons, and those are the tendons that would dive into those shear walls, as was shown in the previous, some of the previous sketches. And on the left, those are PT tendons within a rib, right? And then every one of these PT tendons as part of the construction sequence was stressed. And so you can see here an operator on the edge of the building that essentially has a machine, a jack that grabs one of these tendons and pulls it in order to get to the prescribed force of the tendon. So as I said, we're very close to opening. So the building is intended to be open in April. And so these are some of the pictures, some of the latest images that you can find again online available, and of the building. And with that, just I'd like to again thank you for having me, and I was happy to have a conversation with you today. And if there is any questions now or later, I mean, feel free to reach out.
Okay, thank you very much, Alessandro, for a very fantastic talk. And I think we can open the floor to questions if anyone has any question. Please, yes, Alessandro, go ahead. You can unmute yourself.
Hello, hi, Alessandro. Hi, how are you? We know each
Hey,
other, so
hi.
we have Alpha GT here to support you, Ale.
Yeah.
Amazing project. I mean, I know a little already, but it was a very good presentation. Thank you very much for doing that. One quick question, to be honest. The horizontal movement at the end, the
hmm
width, I'm expecting was quite substantial, the global horizontal movement. Did you think about having additional horizontal dampers to reduce that movement, or was within the expectation and could control it?
Yeah,
Thank you.
good question. So we spent a lot of time, as you can imagine, analyzing, right, the sequencing of casting the slab and shrinking, and we were able, and we studied multiple scenarios, right? I mean, are we gonna let it shrink? Are we gonna lock the end and then let it shrink from the north, or are we gonna lock the north and shrink from the end? Once you pick the center, right? So essentially, you're cutting down a lot of the path. It's the ideal because you lock the center and then you have half the building shrinking one way and half the other building shrinking the other way, right? We were able to resolve it without any additional damping or any additional structural solutions. And it was significant, but still in the order of magnitude where, the isolators could take it, right? So the isolator shifted slightly and it was still within the magnitude where we still had enough movement in the isolators because the isolators were designed, right, for those very, very large movements. And so we were eating a little bit into that, but it wasn't very significant. So we were able to manage it, but it was obviously a lot of time spent in studying it and making sure that we could resolve it that way.
Thank you very much.
Thank you.
Uh, Alan, I see a question, a hand up.
Yeah, thank you very much, Alessandro. A very great presentation. I really enjoyed it. I just have a question about the type of seismic analysis you have performed for the design. I guess it was time history, but I'm wondering to see if what's linear or nonlinear time history and according to which code you performed it. And the the other question would be, I'm interested to know how you dealt with the rotation component of the isolators because it's kind of multi-staged, multi-layers, a pendulum kind of rubbers and isolators. So how did you consider the rotational effects of time histories, particularly for the isolators? Because, I mean, rather than the translation, or if there is a rotation, the top plate and the bottom plate of the isolator can rotate compared to each other. And what happens there? And have you considered that into the time history analysis in somehow, or any idea about that? Thanks.
Sure, sure. Thank you for the question. So, the type of analysis. So, most of the analysis, the lateral analysis, was done in ETABS. So, the ETABS software, and there is specifications that are given in the ASC 7 code, which is the US code that controls seismic design, right? For the analysis that needs to be done for isolators or additional damping devices, right? So everything was done in ETABS. Now, we also had a peer review as part of the process, and the work has to be peer reviewed once we go down the route of performance. What we call it is a performance-based seismic design as opposed to a prescriptive design, right? Well, if you do prescriptive design, you just follow the letter of the code. The code tells you, okay, this is what you need to do, and there is a route there. Once you go down seismic, there is a completely different route, which is performance-based. Performance-based, you have a peer review. The peer review is typically composed by a seismologist, and then there is an expert of seismic. Usually, one is an academic expert, a professor, and then there is engineer who's an expert in seismic devices. So it's a pretty diverse group. And then they're peer reviewing your work, your analysis, and so this is how it's set up. So just to answer the first question, I mean, so it's American code. and we're doing nonlinear time history. So the seismologist would be the one that analyzing the faults of the area would identify what would be the appropriate time histories to use for your analysis. And so all the plots that we're showing, they're all nonlinear time history analysis, and the response would be the time history analysis response. So the time history analysis, they're really tri-directional, right, inputs that you can set up in your model, ETAPS model, right? For example, so you pick XYZ coordinates, and then you can rotate these XYZ components based on the direction of the seismic input that you are considering. And typically you have to consider seven. At the time, we did 7 time histories. Now the code asks you to do 11 time histories, and then you can work based on the output from these different time histories. You either take the average response or you take the maximum response. There's different ways to manipulate then the forces in the data. The most effective way to deal with the isolators, there is the triple friction pendulum component inside the ETAPS that allows you to essentially it's a component, so is an element. Is effectively an element that accounts for with a series of input parameters which are specific to the type of isolator that you're using, and so you can calibrate that element within the finite element to your specific input. So we can get a series of the key critical part is calibrating that element through testing that is done on the isolators, the input from the peer review panel, right? And that becomes the input to that element. And that element then takes into account of all the issues that you are describing, because of course, I mean, you need to account for the rotation. So it's accounted for inside the element itself. Yeah, it's part of the analysis. So that becomes part of it that way.
Yeah, thank you, Alessandro.
You're welcome.
I see, Maher, you have a hand up.
Yes. Yeah. Hello. Thank you for your presentation. It was really enjoyable and informative. So my first question is, so the building footprint is very large and long. Did you consider the effects of differential horizontal excitation on the structure? And my second question regarding the viscous dampers between these slabs. So isn't there a possibility that the top slab could push the bottom one, causing additional bending when the vertical displacement are in phase?
So starting with the last one, yeah, it's possible. So as part of the so we actually model all these dampers, right? And with the mullion and the interaction between the two. And once you model the damper as a damper element, right? I mean, you can still transfer forces, right? I mean, it's a dynamic analysis again that you're conducting as a time history analysis. But you need to account for, yeah, it's possible that that scenarios occur, right? There is a scenario where that happens. So you need to design for those forces when they're in phase, and they could be reversed as well. Your other question was about so yeah, there's no joint in the building. It's a very long building, right? But the seismic input is the same. Essentially, you apply the seismic input to the entire building. Now, there could be, of course, you mean horizontal or vertical differential?
Oh, horizontal in case of many a love wave or
Yeah, correct.
yeah,
Yes, it could happen. Yes, definitely. It could be happen, but it's you would notice it as a result of the analysis, right? That this would occur. So it's part of the analysis process as opposed to we accounted it for it, but we didn't do anything specific on any different than applying the seismic wave to the as input of the analysis. But yes, there could be, depending on the frequency, right, horizontal frequency of motions and the type of input, you could get some, but those are really secondary and more secondary effect, right? The most primary effect is definitely the more noticeable one is just generally the overall average, movement, and the secondary is the relative displacement horizontal is secondary. Now, vertically, of course, I mean, there is the differential displacements between the top cantilever and bottom cantilever because the frequencies they're in, right? So that's very noticeable. And those were primary concerns. The horizontal differential was a little bit, it was minor, let's say.
I see. Thank you very much. Yeah.
You're welcome.
Yeah.
Then maybe a last question from Iason.
Hi, Alessandro. This is Iason from AKT, the party where Alessandro, Edo, and Francesco, we all
Sure,
work
of
together.
course. Yeah.
I was just had a couple of questions. The first one was the location of the bearings at the preliminary design. Was there any consideration to have them instead of the ground on a more elevated position? That's the first question. And then the second question I have is that in AKT, we do lots of work nowadays with the vibration serviceability, and we're trying to develop a performance-based framework for that. Given the length of the cantilevers that you had, was the vibration serviceability from footfall vibrations a problem, or was that resolved by the damper and maybe was in a much smaller magnitude of a problem when compared to the seismic vertical accelerations? So these are my two questions.
Sure, no, thank you. And again, very good questions. Yes, we did consider, placing them a little bit higher. Like, for example, instead of the bottom of the tower, you could put them right underneath the exhibition level. So we consider that. The problem is that then you would have a joint, right? I mean, it would be, you either cover up that joint, right, with some form of, in some ways, architecturally, right? But otherwise, it will be very visible because you're right. You're looking up at the tower, it will be right on the soffit of the ground floor, right? And so that will be very visible. So that was architecturally posing challenges, significant challenges. Not only that, you need to, whatever you use to cover these isolators need to allow for the movement. And so oftentimes, it's very hard to design for, say, you have 2 meters of movement. Can you imagine if you use like an accordion type of joints? They're not very nice. It's very
Okay.
so it was better to bring it down in the basement of the building where then you don't cover it, or it becomes easier to handle architecturally. So it was yeah, but it was engineering wise, yes, you could have a conversation about pros and cons of shifting it higher, but unfortunately it wasn't architecturally it wasn't in many ways possible. The other question, yes, we also looked at vibration, another great point for long cantilevers vibration due to human-induced vibration, from walking is usually a concern. But because, we were mostly controlled by really the self weight, the gravity loads, and because of the post tension, and there is a huge mass, right? You have this concrete mass, and so it was never part of the controlling. We did check it. Like we check many things, but it never factored into as a major concern. And also the fact that we had that damper connecting, the exhibition level with the roof, that also helped, right? I mean,
Okay.
with the footfall vibration, because you had that extra damping into your system, so it never entered into the factor. If we had done it in steel, though, right? If we had steel beams and metal deck, and probably it would have mattered more because obviously it would have been a much lighter system and probably would have factored much more, I would say. But for us, in our case, it wasn't really an issue.
All right, thanks. That makes sense. Thank you.
Yes,
Thank you.
you're welcome.
Yeah, I think we have extended by 5 minutes. So thank you everyone for joining the call today. Thank you, Alessandro, for the fantastic presentation, and I hope you all have a good day. Thank you very much.
You too. Thank you for having me. Take care.
Bye.
Bye.